Hola. Bueno, micrófono impresionante. Hola todos y todas, bienvenidos, bienvenidas a la Facultad de Ciencias Exactas y Naturales, a este evento que es muy importante para nosotros, porque es el primer evento público. Es el primer, ¿me escuchan? Sí. Es el primer evento público del Centro Interinstitucional de Datos. Sí, es un evento que para nosotros es muy importante. Lo que voy a hacer es pasar a hablar en inglés ahora, por respeto a nuestros invitados, a uno que no habla castellano, así que voy a empezar de vuelta ahora. Hello everyone, thank you for coming. This is a very special event for us. It's the first event of a series of Ateneums, we've called them, that we're organizing from the data, I've never said this in English, the Interinstitutional Data Science Center, and it's interinstitutional because it's part of the University of Buenos Aires, but it's also part of the Ministry of Science. And this center was set up, we're functioning we've been functioning for about 2 months now, I'd say in full steam. And the goal of this center is to promote data science and to promote the transfer of data science technology to the public sector, to the private sector in Argentina. So it's not a center that is focused on the science of data science, rather it's a center that's trying to bring together all that the researchers in Argentina know how to do and have contributed to in the state of the art, and actually use that knowledge for the public good in the private and the public sector. In that spirit is that we decided to organize a series of Ateneums rather than seminars, because the spirit is one in which we bring into the center both people from domains that require data science solutions and experts that are capable of providing those solutions. So it is to bring together the problem and the potential solutions and have a discussion, rather than perhaps a usual seminar of scientific knowledge being explained to the general public, but without an anchor on the real problems that we're interested in solving. So that's the spirit, and this is the first of these meetings with that spirit, and I just wanted to welcome you and say that we're very happy to start out here and pass the baton to Enzo. Are you going to continue, or?
Yeah. Or directly to Lucia.
I thought you were going to present Lucia. Okay, so Enzo Ferrante, who's kindly agreed to host this first meeting and will be doing the presentations and taking the questions, etc. So thank you, Enzo, for doing this.
Well, thank you everyone for being here. It's my pleasure to have here 3 amazing speakers today. We're going to start with Lucia. So Lucia is from FLENI, one of the main neurology institutions in our country, for those who are coming from abroad. And Lucia is the director of neuropsychology of FLENI. So she will bring here the perspective of the adoptants of technology, basically based on AI and medicine. And then, after that, we will have Nassir and Alex, who will be talking about the development of these kind of technologies. Okay, so Lucia, thank you very much for opening this.
Thank you for inviting me. I'm honored to be the first speaker of these Ateneums. My idea today is to bring the perspective of the stakeholder, of the medical branch of this collaboration between data science and medicine. So I am the head of neuropsychology. Neuropsychology is one of the sections of the Neurological Institute in which I work. I work in FLENI Institute. FLENI is a very important neurological center here in Buenos Aires. It has 2 sites. One site is here, 5 minutes away from here, and the other site is in Escobar, 50 kilometers away from here. And maybe the more important characteristic of our center is that it has a very broad range of different neurological specialties. So as you can see in the slide, we have like vascular neurology, neuroimmunology, we have cognitive neuroscience, in which I work, we have a department of headache, pain, we have endocrinology, so we have different specialties all linked to neuroscience. Also, we have an imaging center in which we have MRIs. We have 2-3 Tesla MRIs. We have a PET scan with a cyclotron. And we have a department of molecular biology that hosts a biobank. We have a brain bank and a biobank. We have also a department of neurosurgery, and we work with pediatric and with adult patients, both. So maybe to give you more of a view of what the work is in this institution, it has as I mentioned, a broad range of different neurological specialties, but it also has like a very big patient flow. And so we generate a lot of data in our institution. We have around 200,000, I have to read it, medical consultations a year. We have 35,000 MRIs a year. We have more than 1,000 neurosurgeries. And in my department, we have more than 500 cognitive assessments a month. So this accounts for a big volume of data that is generated, and most of the time this data is used independently, only in patient care, only to give the patient a result or to provide the patient with a treatment. But we have the idea that medicine and computer science should not be two isolated disciplines, and that should not be thought about two concepts that should be bridged or that we should build like a crossroad between them, but they are like Dr. Fei says, like two sides of the same coin. And we have to learn to recognize this coin, to trade with this coin, to spin the coin around in order to really work in an interdisciplinary way. So the work and the collaboration between medicine and related disciplines and computer science can help us improve our outcomes, improve our treatments, improve the quality of the diagnosis. So this is what we are trying to do in FLENI. We have started only recently, a few years ago. This is an initiative built by Dr. Fernandez Lezac and Mauricio Fares, and also in collaboration with Dr. Chavez, that I think he's here from FLENI. They designed this project, ENTELAB project. This is a neuroimaging analysis program that helps us have faster and more precise results about the neuroimages of our patients, and really ensembles the work of computer science with medicine. This has been implemented in our institution and is used in many of the neuroimaging procedures that we do. Another of the tools we use is the Rapid AI software, and this is a software that helps us with vascular and neurovascular neuroimaging, and it helps us recognize which tissue can be regenerated in a very few minutes and with a lot of precision. So our vascular team is working with this software. So today I wanted to take the opportunity to present this first collaboration between the CID, the Center of Interinstitutional Data Science, I think that's okay, the CID and FLENI. So we are collaborating in the Latin Fingers project. The Latin Fingers project is a project designed to prevent cognitive decline and dementia across Latin America. This project is inspired in the original finger. The original finger was founded the first time in Finland, and it recruited 2,000 participants and randomized them into a control group and a treatment group, and the treatment group received a lifestyle intervention. So it's a non-pharmacological intervention in which these participants who were at risk of dementia tried to change their lifestyle in order to prevent cognitive decline. The results were amazing and very significant, and were more important than those that were achieved by the drugs, the pharmacological treatment at that time. This was 10 years ago, and still now the results are more significant than those. So this inspired a worldwide network of worldwide fingers trials. So we have trials in Canada, we have trials in the United States, we have trials in Australia, in some countries in Africa, in Europe, in China, China. Each one has its name, and each one has been harmonized to be respectful of the culture in which it is implemented. So I will talk briefly about our project in which we are collaborating with the CID. This is the Latin Fingers project. We have 12 countries involved, and this initiative is coordinated from FLENI from Argentina. The countries are from Mexico to Argentina, including Ecuador, República Dominicana, Costa Rica, Uruguay, Colombia, Chile. So it's a very heterogeneous sample. We are trying to recruit, well, we are very recruited. We are more than 98% over the recruitment period already. 1,200 individuals, 100 from each country, and we randomize them into these two interventions. And the idea is to follow them up longitudinally in 2 years. And the outcomes are feasibility, to test if this is really possible in our region, and also efficacy. So the eligibility criteria are people in risk of dementia because they have cardiovascular risk factors and a diminished cognition, but they don't have mild cognitive impairment, they don't have dementia. So they are in risk of having that. And as I said before, they are randomized into two interventions, a flexible intervention that is basically the control group who receives regular health advice about these 4 things that they should do, and a systematic intervention in which people are trained to do physical exercise, change their nutrition, do cognitive training, and control their cardiovascular risk factors. So, regarding data, the data is being hosted in a unique database and will be analyzed by the CID. They are now monitoring the data, the recruitment of the data, and they will be then analyzing the results. We have cognitive outcomes, we have clinical outcomes, socio-demographic outcomes, of course. We have a biobank that includes DNA, blood, plasma, and we have MRIs that follow the ADMI 3 procedure, but also we have some centers, 2 centers have only 1.5 Tesla equipment, so they are following a more basic protocol, but that is comparable to the other one. And these are the times in which we test the participants. We test them, all of them at the beginning and at the end, in all of the variables, but some variables are repeated throughout the trial every 6 months. So, to explain a little bit why we chose to present this, the idea of Latin Fingers is first to generate data that is locally relevant, and also it is in which the protagonists are Latin Americans. So we have a 2-year embargo to analyze, to work with the data ourselves. The idea is to promote, to encourage, to motivate local researchers to test their own hypotheses. But after that, the data will be shared worldwide. We will use the game platform, and the idea is to do something similar to what has been done with ADMI, to share data and to let everybody test their own hypotheses, compare our sample to those of other regions, and to generate knowledge that is democratically distributed. So to end, I wanted to find a nice quote, but then I remembered about this fable that it's attributed to some Hindu tradition. It's a fable, I don't know, maybe some of you know it. It's about 6 blind men who approach for the first time an elephant. So one touches the leg and thinks it's a tree. The other one touches the trunk and thinks it should be a snake. The other one touches the ear and thinks it's a fan. And the one who touched the horn thinks it's a spade. So everybody is limited by their own perspective and their own experience. So I think what we are gathered together to discuss today is how interdisciplinary work can bridge this gap and can help us look at things holistically and discover all of the mysteries of human mind and of human brain and of our health in a more complete and comprehensive way. Thank you.
Thank you very much, Lucia. You want to stay just for a few, 2 minutes, just in case there is any questions from the audience about the project. Amazing project, by the way. I didn't know about it. Sorry. Otherwise, I have one question.
Okay.
So in this initiative that you are creating, what kind of image modality? Because you mentioned MR, but are you also considering like PET or also a functional MR, like a resting state, like in order to?
So we have 2 protocols, and the ACNI 3 and the ACNI 3 protocol includes a resting state capture. So we are using fMRI.
fMRI,
well, resting state is like an fMRI paradigm. So yes, we are using that.
Okay.
And we are also applying for funding to do biomarkers.
Mm-hmm.
So that's the idea too. The blood biomarkers in the population. Thank you.
Alex?
Yeah, there is a question connected to the interdisciplinarity point. One thing I found in our area, in our institution that is very important is cross appointments between medicine and engineering. Is there any plans in the context of the center here and organizations like FLENI, but potentially others as well, to have people who are affiliated but at the same time, bring those multiple perspectives?
It's a very interesting question. We've been discussing that with Diego Slesak, and his proposal was to bring people from FLENI to their practices here and to start participating in the Ateneums and in the seminars. So now we have a project that is inspired on natural language processing, in which we are collaborating, and people from my team, from the neuropsychological team in FLENI, are coming to here to the artificial intelligence lab to test the patients here. That's it. The idea is to collaborate in that sense. Okay.
Any question? Okay, then we thank you so much. Okay, and now our next speaker today will be Alex Frangi. So Alex, for me it's a pleasure to have him here. Maybe some of you know, maybe some of you don't know. First of all, Alex is Argentinian, and but he will be speaking English just to make it understandable also for Nassir. But we are organizing here in Argentina next week, for the first time in Latin America, a big conference that is called IPMI, Information Processing Medical Imaging. We are really happy about doing that because, well, it was a plan that Alex proposed me some years ago, and we started this, and this is just happening, like, starting on Sunday. And so, when we were discussing with Diego and people here at UBA, we say, okay, can we take advantage of Alex, Nassir coming also to Bariloche, and they maybe stop over here in Buenos Aires and come to the seminar. So that's how actually we ended up having Alex and Nassir here today with us. So maybe some of you will go to Bariloche next week. I'm seeing Martin there, I think he's going, so that's great. And yeah, so this is just for you to know how excited we are about that. Now, well, Alex is a professor at University of Leeds, and he in the UK. Before that, he was at University of in Barcelona as well, and also in other cities in the UK. He has been all over the world, and he's one of the founders of many interesting fields actually in which we are working today. I mean, I've been reading Alex's papers since I started my PhD, and it's really amazing to have the opportunity to have him here today. Actually, he has even a filter under his name, right? The Frangi filter. Maybe some of you use this for vessel requirements. So it's really exciting to have him here. So Alex, the floor is yours.
Thanks a lot. When they call you founder of something, is another way to tell you that you're becoming old. Okay, so is it?
Yeah, we shut up.
So it's a pleasure to be here. So indeed, I'm from La Plata, so I've just come from having visited with my mum and siblings, and I think it's quite important this initiative that is being set up with this center, and in any way that we can collaborate, that would be great. So as Enzo was saying, this conference that we're organizing in Bariloche is actually sort of a dream between Enzo and Demian, who is another Argentinian who is in France, and there is quite a lot of us around out there, and in any way we can help, we really would appreciate doing that. So what I want to talk today is about the use of imaging and modeling to do something that perhaps is not directly benefiting diagnosis or treatment, but is very connected to improving healthcare, which is the regulation of devices, medical devices, imaging as a medical device, but also implants as medical devices. And I'm going to try to explain you why this is important and what the role of data science is in this, and then some of the results we have. And I may be skipping stuff as we go to just make sure I keep the timing right. So first I'm going to explain to you what precision computational medicine is, which is the area where I work. And some of the names here are going to be colleagues that I work very closely with, and you see that they are all very international. So Sig is an Australian, Tony is actually a Finn, and Nishan, as you could guess from the name, is Indian. So one thing that has inspired me for a number of years is this pyramid. This pyramid is known as the DAKY pyramid, from data, information, knowledge, and wisdom. And what it does say is that it's great that we have lots of data nowadays. That's just the beginning of the journey, because unless this data is contextualized and transformed into information, that is sort of curated into knowledge, and that is tested over and over again in a number of studies so that it becomes what we call wisdom or validated knowledge, only then you can start taking decisions on the basis of this. So wisdom in medicine would be a guideline, for instance, a medical guideline. Data could be, the measurements of an MR scan, and information is when you know where particular anatomical regions are and the volume of them are. And knowledge is when you realize that there are thresholds above which that volume becomes problematic and is connected to disease, right? And there are two ways to do data science, in my view. One is what we call phenomenological models, so models that are bottom-up or data-driven, and things like deep learning are in that category. But also you have what we call mechanistic AI, or techniques which are based on first principles. And that may not be so fancy like deep learning nowadays, but there are things like numerical modeling, where you actually can code the equations of physics or biology or whatever your priors are. And we've done it, I'm going to skip this, but there is a few papers that we wrote trying to explain some of these ideas that I would be happy to share with you. Now, the difference between phenomenological and mechanistic models is that this is limited by data, the phenomenologicals, while the other ones are limited by the theories you have, the knowledge you have. And this is limited by the sampling of the data you have, so you may be sampling only a corner of your space. Like, for instance, we were discussing with Lucia before, you may know things about the brain, but only sampling the Americans and the European populations, and then how much that it tells us about South American population, for instance. While in this case, you're limited by your theory. And this is to me a fundamental plot, which is quite important. So this is work done by a guy in Switzerland, who is a Dutch guy, in ETH, that he has a plot that shows as we go over the next few years, how different things will change. So the blue curve is the processing power, the Moore's law, and we know that it's an exponential and doubles every 18 months roughly. And then we have also the, let me see if I can get this way. Then you have the green curve, which is the amount of data that we're collecting, and this is modeled as an exponential, but doubling every 12 months rather than 18. And people say that in the coming years it will double every 12 hours, but it's an exponential. And the important thing is that when you have two exponentials with different rates, they cross at some point, right? So there will be a point where data we will have we won't be able to compute it because we don't have sufficient computational power. The killer one is this red one, and this is the complexity of the systems we're trying to understand, or the systems we use to understand them. So the number of parameters we have when you look at about a neural network, how many coefficients there is, or for instance, in Europe, there's a lot of emphasis being given now into comorbidities. We always study diseases separately, but actually there's a lot of interconnections between them. And we tend to sort of ignore all those interactions. But when you start putting them, the picture is very, very complex. So the number of parameters you need grows factorially as we understand diseases, we get better basic science. So the position is pretty crazy. At some point, we will have systems that we're trying to explain that are more complex than any data we will be able to collect, and far beyond the capabilities of our computational resources. Okay? So how do you sort this out? Well, you need to incorporate priors, because that's what reduces the dimensionalities by putting prior knowledge. So you can't do things purely data-driven. You need to build the understanding, and we're not going to go into a lot of detail of that, but there are a number of deep learning techniques that actually allows you to put some of these priors. Now, that's something we are very interested in. We have in the back of our mind when we do all of our research, is how we can incorporate those priors as well. Now, I'm going to talk a bit about regulatory science. So, regulatory science is the science of creating methods, tools, and systems to generate better regulatory evidence. And regulators fundamentally want to know two things about any medical product, from drugs to implants to imaging. They want to know that they are safe, so that you're not putting people at risk, and verification, so that actually they make a difference. And there is a balance between these two. Now, the implant false studies, which is a study that run by investigative journalists from 2008 to 2018, demonstrated that there was a number of the implants, all of which went through regulatory approval by FDA, that produced in the order of 83,000 deaths and 1.7 million serious adverse effects or injuries on patients. This is in the US. Okay? So our way of doing regulations and ensuring safety and efficacy is not good enough. And I could tell you about a bunch of consequences of that, from risk on patients to the fact that this is going to be even more complex as we go, because also the complexity of the therapies is growing. An implant used to be a piece of metal in your hip. Now they have biochemical coatings. They have also sensors. There is signals that are propagated, and we need to do AI with those. So these are very complex type of interventions. The other thing is that every time there is a recall from a medical device from industry, is a 10% drop in their shares the next day. So to give you an idea about the impact on economically as well. And in particular in the UK, they're very concerned because with Brexit, in the end of the day, there's 70 million people. It's not a massive market, right? And companies want to have global approaches to address those issues. So what is happening is most of the trials are going away from the UK, and they're going where? They're going to Asia, where it's cheaper, the manpower to run them, or to the US, where the regulatory pathway is a lot clearer. That's not good, because you're generating evidence on the basis of demographics and not your answer. To give you a bit of an idea, this is this plot here on the top, the upper curve. So this is the last 20 years, and this is the growth in the market for drugs and for devices is growing between 5 and 6%. The automotive sector is growing at 5% year on year. And this is the amount of drugs and devices that are approved by FDA on a yearly basis, flat over 20 years. So we have a lot more demand, but not good supply. And part of the problem of supply is that it's very costly. Producing a drug takes 15 years, producing a device is between 7 and 11, and is a billion operation in the case of pharma, is several millions in the case of the device. In the UK alone, 1 of 5 SMEs is going to do their first regulatory approval to the US at the moment, because of that confusion that is being generated with Brexit. So what do we mean then by computational medicine or in silico trials? Computational medicine is using engineering and mathematical and computer science approaches to understanding disease and designing better interventions. And in silico trials is the use of computational models. So we talk about in silico because of computers that build of silicium, as a counterpart to in vitro, in vivo, in situ. And what we try to do is develop computer-based tests or trials, environments based on mechanistic models that actually are highly controlled and that allow us to describe a population in a very meaningful way. Now, this is not completely new. If you look at the aerospace industry, we're doing actually this for ages, and we have very sophisticated multi-scale problems. They're highly regulated, and there is a tendency to go from the physical to the virtual space. And here is dominated by the fact that you simply can't just build planes and then sort of test them as we do. Because the clinical trial ultimately is a glorified trial and error method with a bit of science around to make the sampling correct. Automotive industries, the last 30 years we've gone, from these cars to these cars. The product is better, but the process is better as well. So we don't do wind tunnels anymore, with wind tunnels. We do aerodynamic simulations. We don't tend to do physical crash tests as much. We tend to do, computational crash tests and virtual prototyping. We also talk about self-driving cars and inclusion of AI. So what I was wondering for a number of years is why on earth we don't do the same in healthcare, where it's actually the most exciting area where you should be applying this. So if I show you, so one of the areas I work is in neurovascular implants. I'll talk a bit about that, which, FLENI has a lot of work in that space, with Pedro Lilik and other people in there. And if you talk to these guys, any neurosurgeon, over 20 years, essentially the development of the product is a bunch of wires, seen from an engineering point of view. They went from coils, which essentially slow down the flow and produce coagulation, to then coils with a stent, which usually they started with sort of coronary stents, which are open cells, to deal with the problem of wide necks. And then they now put some very tight flow diversion devices that redirect the flow without the need of the coils. But essentially it's similar materials and not very, very sophisticated. We still have 20% failure rate and about 3% death rates in those patients, and we could do simulations like we do for the aerospace. We can tell you for a particular virtual patient what will happen if you put the stent in one way, and the other way if you do it across a stent. And it's very different what happens with each of them. So you could use these tools for personalized therapy, which is what Pedro and others have been doing. Juan Sebral as well in the US, who's another Argentinian, by the way, in the US. What we are proposing here is to use the same techniques, but for the early phases of designing of the device. And if you look at these plots, if you look at just the black plot, this is what we do today. This is the whole cycle, the life cycle of the product, from the discovery and idea of the device to the trials, to the post-marketing analysis and evaluation. So what we do in this space, we don't do a lot of testing early on because it's expensive. Each test for the device could cost you £100,000 on animals. And how many devices, different versions of the same device you're going to try? Maybe 6, 10, but you can do hundreds of them. For hundreds of them, you need to do 10, 20 animal models, each of them 100K, each of them. It's just crazy. And you don't even know whether you have a product at that point. So what they want to do, companies want to move very quickly to the preclinical trials and trial space, because that's the proof of the pudding, does it work or not? But then when it doesn't work, you need to go back to the drawing board, and that's very, very expensive. Because as you move into the pipeline, every error, everything you need to fix is more and more expensive, okay? And if you go into a trial, and you need to recall a trial, it's crazy, because you may have to pay legal taxes for people that, is treated or whatever. So what we are proposing is this purple line, which is what we call upfront simulation, where you can, in virtual populations, create the testing much earlier on, so that you only move to preclinical and human testing there with the designs that you know are the most reliable ones. So let me put this a bit in picture. So imagine you could have a library. Imagine, Lucia was talking about 35,000 scans per year, right? That they do. I suppose most of them from the brain, but they would have a cardiovascular center somewhere, right? And a similar center for other areas. If you could take all those populations and build anatomical models of the heart, the brain, whichever organ you're interested in, you could build a library of models that come from real subjects, right? So here I give you a subsample from a library we have of brain aneurysms. Now what you can do is for each of them, and I'm not sure if you can see this in the plot, but you should see a stent somewhere here, right? In the figure. So these stents are virtually implanted into that 3D model that we have. And I just showed two to show two different anatomies, but of course we do that for the whole database. And then you need to come up with a surrogate outcome measure, which in our case is the flow reduction. So how much the flow within the aneurysm was before we put the stent, and how much the flow is after we put the stent. Because that flow reduction is a proxy for clotting, and it's a proxy for closing the aneurysm. And if you pay attention to these numbers, you will see that they go up and down a lot depending on what we do. Now, we also can have physiological variables, measures from medical implants, or from wearable sensors, where we can identify how much these people vary over time. So some of them will be more active, some of them will be more sedentary. So we can create models of a heartbeat, in this case, and if you can see that there is a thick line, which is the mean, and then there is a cloud around that, which is the variability over 100 subjects that we tested. So these are Gaussian process models, if you're curious. But where we can sample both the blue state, which is people at rest, and the red state, which is people at exercise. So this we did over a 48 hours Holter system that we were measuring over 100 people, and then what we did is we sort of calculated means and variances of those populations. So you can now take, say, the anatomy from one of these subjects and see what happens with the same patient in rest and stress conditions, and what is the response. And then, of course, you can put different devices and compare them. Okay? Now, if you look at this from a bigger perspective, what we have is an in silico trial is a massive simulation space where you have different axes for anatomical variation, but other things like mechanical properties. Also another one for lifestyle, physiological variability, operational envelopes, so you can model, for instance, the influence of the operator in putting or taking the catheters by some sort of, well, there are mechanisms to track those and do models of those as well. And of course, you can put different type of devices and look at the optimal one. So if you now put in every node like from here, a color that represents how good that device is for that combination of circumstances, what you create is a map, a heat map that tells you that a particular device, which is the group of patients for which it behaves the best. So you effectively have an inverse readout of the diagram, which is an stratification chart. Okay? Now, where do we get the data? Well, with biobanks, I'm not going to go into the details of the ones we use, but I'm sure that you have equally good ones in Argentina that actually would allow to create populations which are adapted to the circumstances of the country, or a particular demographics. So, what do we need for this? An in silico trials is basically a way to generate virtual populations. This, for those of you working on deep learning, is generative models and synthesizers. Ways to do virtual examinations, imaging, or virtual interventions. So these are fundamentally biomechanical models or physics models of the acquisition of imaging. We know the physics of acquiring pretty much every imaging modality nowadays, and if you have the anatomy, you can model the physics of absorption of X-rays or attenuation of ultrasound waves or whatever. And finally, we also need a mechanism to do virtual readers or virtual outcomes. But a virtual reader isn't that an algorithm of AI, again, reading to an image and doing a prediction for a given pattern in the image what the outcome might be. So behind all of this is a huge amount of data science, there's a huge amount of deep learning, and a huge amount of
computational physics and computational mechanics as well. Okay? So what do we mean with all this? What is the vision of this? Well, it's not to remove the need of clinical trials. I believe we need clinical trials still, but we need them as confirmatory tools of a good hypothesis. What I believe is that we shouldn't allow clinical trials to progress before you have evidence through computational trials that there is any hope that that trial will make any good to the patients. So it's almost like a gatekeeper. It's a gate stop for bad innovations. I'll give an example in a minute. And more generally, you can use them for reduce, replace, and refine. So if you, for a computational trial, you can get an idea about the magnitude of the effect you're trying to measure with a human trial. You can do sizing better. So you don't have a trial that has to be aborted because it was underpowered. And you can also, in some cases, replace. And given Lucia's interest in neurosciences, I will bring one example from Medtronic, where they developed some electrodes for Parkinson's disease. And one of the questions the regulators asked to them is, are these leads going to generate heating, right, with all the implications of that? How do you do a trial to demonstrate that? So what they did is they validated through animals a model for heating, and they show in 1 million different possible configurations of these electrodes that the heating profile on the brain was well below a safety margin. And the guy who developed that, and I know he's currently in Oxford as a professor as well, he told me, look, not even today, this was like 20 years ago, not even today we have implanted 1 million of those devices. Medtronic has implanted 1 million of those devices. So they don't have even today the evidence on real subjects. Okay? So in the future, the regulatory evidence will be a blend between the evidence that we have through animal, through human, through computational trials, and through bench studies. And ultimately, what you need to realize is that all of these are just models. So a human trial is not more of a gold standard than a computational trial. It's a model that has certain limitations, and you need to accept those. And it may be that the limitations of one approach versus another approach, clearly rule out in favor of one or the other at a particular time. So let me give you a bit of some examples. One example that I will go in a bit more detail from us, and then examples that come from other people in the world that are working along the same lines. So this is a study that I'll talk later a bit more in detail, but it's about aneurysms, intracranial aneurysms. These are the type of stents or flow diversion devices we develop as a population where we can control the physiological regime, we can control the anatomy, and we can control also a number of the characteristics of the population. Because if you have a large database, you can apply inclusion and exclusion criteria like in a trial and create a subpopulation that is alike the one of the trial you're comparing against. This is another example. This comes from Zimmer Biomet, which is another medical implant company in Switzerland that is focused on musculoskeletal implants. And one thing you need to do, we talked about bench testing as well, not only human testing. So they do cadaveric tests. So this is a piece of the femur, I suppose, from a cadaver, and they need to sort of put the anchoring system of the implant where then the ball basically goes. And one typical thing they do is do a stress test, is where they put into a machine and they look at what is the breaking point of those, right? Now, those tests are very, very expensive because you need to mimic situations of the real walk. And what they do is they put into a machine that emulates, gait cycles. But they do it, say, times 10 to accelerate time. But even if you need to demonstrate a 10-year survival, even if you go 10 times faster, it's 1 year in the machine that you need it, right? So again, there are ways in which you can do these virtual tests through computational mechanics. This is another one from J&J, the PUI Synthes, which is another company from J&J in the US on MSK. They work with the University of Bath in demonstrating that something which is a combination of a device and osteotomy, if I'm not mainly in this area, but I understand that it's essentially removing a slice of the bone so that they can correct the bone to be straight. So without cutting the slice, the person is walking like a bit on the side. By cutting that piece of bone and repositioning, the person can walk straight again. To hold things tight, they put this piece of metal But it's a combination of a procedure, so how much we take out, plus a piece of metal and the supporting evidence. They run a trial, a computational trial, and on the basis of that evidence, they are now running a human trial that is a confirmatory one. And then this is from FDA, so FDA themselves are doing research, and they have an example where they compare digital tomosynthesis with, breast tomosynthesis with digital X-rays, and comparing the equivalence of the two techniques, because one is more expensive than the other one, so it's a test of equivalence to make sure that then they can look into cost effectiveness. And they've done lots of work in that area demonstrating the equivalence of the two, and they published an interesting paper that the title is quite telling. It says that these techniques are faster, better, safer, and also more scalable. Because you change a parameter now, and you can rerun the trial with the parameters changed, rather than having to run a whole human trial from the get-go. So, just to finalize, let me give you a bit of an example in the area of the first one that I showed. So this is about aneurysms. There are aneurysms in the brain, are basically bulges that are generated around the vessel. People don't fully understand why they happen, whether it is degenerative or there is a genetic composition. There is evidence in both directions. And they like to appear a lot in the bifurcations because that's when you have the more disturbed flows. And then there are different ways to, and this is a time bomb. I mean, you have one of those and they burst, a third of the people die straight away, a third have high morbidities, and a third sort of makes it through. And there are different techniques. So you can do clipping, which removes craniotomy. So you need to open the skull, put a clip at the base, and reclose, which takes a long time in the hospital. And then there are the plunder ways, or the minimal invasive ways, where all of them start through the groin, through an incision in the groin, and then go up under image guidance all the way to the brain with catheters. Okay? And from those, there are different types. We can put coils. This was, by the way, invented, I think Guglielmi was Uruguayan, right? So he was an Argentinian, but I met him once in UCLA. So this device is called Guglielmi detachable coils. The way they work is you put a coil inside, and then you pass an electric current that detaches. It's like a fuse. It sort of burns the fuse, and then you can take the rest of the catheter out of the body. And all of these devices, what you do is you put something that slows down the blood. And we know when we have a wound, that what do we do? We just try to press, because when we do that, we clot, right? So they put that, but if the neck is very wide, then these guys can come out. So what you tend to do is you put a stent, and the first stents they used were coronary stents. Later on, they realized there was a number of issues with those. Then they sort of developed this new generation of flow diversion devices, which are much tighter. Okay? Well, I'll tell you now why you cannot put a graft, like in the aorta in a minute. But there's tons of those. There's tons of these devices. So it's not like one type of device. Just for doing this, maybe there are 20 being developed. So imagine, each of these 20 has to go through the trial, has to go through human testing. That's why medicine is brutally expensive. So what you do is you put the device and you generate the slow reduction, you produce a clot, and eventually you reduce or remove from the circulation this guy. There are also other vessels called perforators that you don't want to mess up with them because they're the ones who feed the brain. So your brain needs blood, and if you close one of those, you produce an ischemic stroke, which is not any better than these ones, which are hemorrhagic strokes. So these are for bursting, others are for blocking. Okay? Okay, so this paper here in radiology was what is called a pivotal trial of the device we're going to study, which is a device from the trunk. A pivotal trial is a trial after which you can go to market. Okay, so before that you did probably 5 years or 6 years of research. After this trial finishes, which is another 5 or 6 years, you can go to the market. So this device took 8 years from design to publication, 6 years of recruitment, 108 patients, not a big whoa number. So when you go to market, you only know efficacy and effectiveness on 100 people. And probably they burst between 20 and 40 million pounds to actually do the trial. And you only know the outcome 8 years after you develop the technology. With a fast pace in technology development, it's too late. By the time you know the outcome, it's too late. So this device is claimed to be one of the most well studied. There are 3 studies we're going to talk. The POOFs is called this one, the Premier and the Aspire. All 3 trials, if you put them together, you don't get 500 patients. Okay, that's all the evidence. The first trial, POOFs, was with let's say middle-sized aneurysms. They did Premier for a smaller aneurysm, so you just have a smaller size, and you need to go through the whole thing again. And then Aspire is a registry. So what we developed is a system. So this is to do this trial. For that, you need a pipeline. So if you remember my hypercube, every node, we need to do all this exercise here. So we need to start from the images, create a segmentation of the image, do a mesh, a volumetric mesh, so you can solve the physics. You then need to put the device, which is another type of algorithms. You set physiological boundary conditions, so the inlets and outlets for all the vessels are relevant. You solve the Navier-Stokes equations that explain the physics. Then you have a map, a new image, which is a virtual image of the flow, and then you solve the biochemistry on top of that gives you the clotting pattern. Okay? Lucía was talking about interdisciplinarity. Well, we have in the group people who are biochemical engineers, aeronautic engineers, this whole zoo of different specialties. Now, we didn't have access to the trial, so we couldn't do comparisons subject to subject, because we never had the subjects in the first place. But we had a population that we could check as a cohort, that we had the same demographics, the same statistics than the population. And I'm not going to bore you with that, but this slide essentially is making the point, and this one as well, where we show all the different characteristics of the trial that we developed, which we call FDPAS, and the 3 trials that I was talking before that we compare against. These were our gold standards. And then what we showed is that we could reproduce to a 5% accuracy the efficacy metric. So this is about 75% what all the studies gave. I think this is a slide better. And we got a 75% PD is pipeline endovascular device, which is the device itself. And by efficacy measure, what we had to do is replicate angiographic occlusion. So normally what you do with these devices is you put the device and then you do a flush of contrast and you see that there's no contrast coming into the aneurysm, right? So you can do that computation as well because you can solve the transport equations of the contrast agents and make sure that there is no contrast coming into the aneurysm as well. And then I don't know if you can see it, but there is something engraved in these plots. It says, I think it says 83 and 67. So the 75 is the overall efficacy. But because we have full control over these patients, we could say, okay, the 88 patients we have, make them, all of them normotensive. And then make the same guys, all of them hypertensive, because we control the blood pressure. And what we show is that if you make them all normotensive, your efficacy grows to 83%. If you make them all hypertensive, it goes down to 63%. This is something that nobody had studied before, because if you had studies with 100 subjects, there's no way you can stratify for, well, actually, they don't even measure the pressure in many cases. So this is quite important in terms of the clinical impact, because it tells you that if you do a pretreatment of these patients for their hypertension, before you actually put them to a surgical procedure, you may get better outcomes without touching the device, the same device. Okay? Yeah, so these are all the plots. I'm not going to go into that, but we looked into the presence of branch arteries, also what happened with giant aneurysms that haven't been studied, what happens with aneurysms with a very high aspect ratio. But the thing I want to comment is that in silico trials don't only tell you what you already know from the conventional trial. You can make extrapolations for things that I would like to convince you there's no way to do it with the conventional trial. So do you remember the story of the side branch? And that you don't want to mess up with it. So there is people around there in the community that say if you have a side branch, you don't put a flow diverger. It's not recommended to put a flow diverger. But nobody really knows why. They know that if you do, you sort of complicate things, but it's not clear why. What we show is that if you look at this patient K3 and case 4, case 3 and case 4, if you look at the geometry, it's the same. Geometry, the same subject. Well, one of them is normotensive, the other one is hypertensive. What we show is that in every single one of the 27 cases we had with side branches in the 88, every time you had a side branch and a hypertension, all the time the clot ended up coming into the side branch as well. While in the cases that were in the same cases, when all of them were normotensive, you don't have any, you don't compromise the patency of the side branch. Okay? So fundamentally what is happening is that in this case is the hypertension combined with the side branch which is generating the problem, not the side branch alone. What you do with that, that's what, device manufacturers need now to think, what is the best approach to correct for this potential. And just a final, to show you another device, because you say, well, that's easy, it's a tube. And so this is the other device that I was talking, is coils. Coils are memory alloys, so you can pre-shape them with a particular, you can pre-shape them, and you can keep that memory of the shape, and then you put them into a guide wire, and therefore they become, straight. And when you release them slowly, they retain the shape they had before when you do the pre-shaping. So you can get things like these or things like these to do a better filling. Okay? So one parameter that I'm going to talk in a moment is what we call packing rate, is the amount of metal, the volume of metal divided by the volume of the aneurysm. So a 20% packing rate aneurysm means that you put metal, multiple coils, up to 20% of the total volume. Okay? And I'm going to focus on this. I mean, there are some devices that also have hydrogels to actually promote coagulation, but I'm not going to get into those. So we developed a technique that actually is, from those of you who are from computer science, is essentially a Dijkstra type algorithm or a minimum cost path, where what you do is you think this as a crawling worm that sort of walks and tries to, cannot go through the wall of the vessel, so it needs to sort of turn around, but cannot self-penetrate against itself. So it sort of feels, using some heuristics, and we've done loads of validations with histology and with flow dilution curves. That I'm not going to go through. But what I'm going to show you here is the following. And how do you model these guys where they end up? This is a stochastic, right? It's random. Well, think about this as a random thing. It's like a random field. So let's look at that in that way. So every row here, every column represents a different packing rate, 20, 25, I think, and 32, right? So you see that already with 20, they're pretty filled. Okay? And you rarely can put more than 30+% because you sort of over-pressurize them first. So each of the colors is because they come with a length and diameter, so to fill it, you need to put a number of them. There's about 1,000 pounds each of them, and you put between 6 and 30, so if you can save 3 or 4 of them, it's lots of money. But how many you put? That's the question. So each of the columns is this percentage, and each of the rows is like a realization of a random field. So effectively what I do is I put coils to 20%, I take them out, which I couldn't do in a real subject, then I put them back again, they will go into different directions because it's stochastic, then I take them out, I put them another way, that's the number third, and you can do it as many times as you want, okay? But what is constant is always 20% filling, and the same is 32 and 25. So what we show is that if you do a curve like this, where this is filling rate against flow reduction, so flow before you put the coils and after you put the coils, when you have a low filling rate, there is a chaos. I mean, you can get almost every value. But as you start getting to higher filling rates, there is an asymptotic convergence to around the margin of values. And then it doesn't matter anymore how exactly you put them. What matters is that you achieve that point. And that point is patient-specific. Some people need more and some people need less. So we did this paper, and 10 years before our work, there was this other paper, this table from another paper, where they showed that aneurysms that were stable have always larger packing rates than aneurysms that were unstable. But unstable, what we mean is that there is a recoiling motion. These coils sort of float out, and you need to sort of fix it again. And you see that the percentage depends on whether the aneurysms are small or large, so they are, of course, patient-specific, but they did that with just 3 different categories. Okay, so we could have known this without actually having to do all these studies. Yeah? Okay, so I'm going to go now to the end, and to say that there is quite a lot of people in the UK that we are working in trying to mobilize this, because it's not only interdisciplinary, but it's also cross-sectorial. We need to work with regulators, with clinicians, with industry, with academia. So there is a webpage in silicouk.org that you can just watch, and there's a Slack workspace, and we have about 1,800 people at the minute that are, and I'm working with them in terms of trying to come up to some sort of consensus about what to do. And there's a number of reports that we have produced there as well, which has been actually quite exciting. Some of those are these ones that I'm presenting here. So with that, I'd like to say thanks. We have a large team. There's a few Argentinians that have passed over now as well. And if there is any one of you that has interest in this area, I would be very happy to have a chat, follow up on that. Okay? Thank you.
Thank you, Alex, for the amazing talk. Well, the floor is open for questions. Is there any question there? Nassir?
Amazing, Alex. It's really interesting, and I'm following it. How much of this?
Sorry, Lucia.
You want to wait.
That's the problem. That's why I don't really use
Thanks a lot for the talk. Amazing work. So one question I have: how much of this is data-driven versus knowledge-driven? How do you do this balance? Because when I look at it, it's amazing, but it's really both of them. And how do you do that? What would be the proportion you need in order to go further?
I think it needs to be challenge-driven. So it needs to be challenge-driven. So basically, use the best you have and not be fundamentalist of the tools you use, but fundamentalist of the problem you want to solve. So if I have a couple of minutes, I can show you some glimpses. The part that I didn't give of the talk is where I actually explain a bit more the methods that we use, or at least some of them. But for instance, this is a pipeline that you need to actually generate, to go from the image to have everything ready to run the fluid dynamic simulation. So the CFD is finite elements, and then we are doing sort of mechanistic models. This is purely data-driven, so you need to segment. I don't even tell you how we segment, but that's another deep learning algorithm. And then you need to compute center lines. You need to compute the point where you need to segment the aneurysm from the vasculature, so the red bit from the gray. You then need to segment the inlets and outlets. You need to know which ones are inflows and outflows. You then need to know where the neck is, so that you can then deploy virtually with another algorithm the stent. And then you need to do mesh generation for hexahedral meshes for actually running finite elements. You need to know the inflows and outflows, because then you need to know, how you're going to put the boundary conditions to your CFD, to your fluid dynamics. All of these steps, they're little ones, and you could do it by hand. The problem is I want to run this on thousands of aneurysms, because I want to have, I'm not going to be happy until we don't have at least 2 orders of magnitude bigger than a conventional trial. The study that I showed with 88 subjects, when you have a trial of 100, that's fine. But we are developing now to be able to have that on thousands of subjects. And that brings a host of new issues. So all of this is deep learning, is data-driven. There is no physics here, right? But for instance, in the whole validation story, for instance, how you do automatic labeling. So say that I tell you that the aneurysm is here, then that tells you that you need to put inflows and outflows corresponding to that part of the circle of Willis. This is how this part of the brain is called, which is very different than if the aneurysm is here. But if you are a radiologist, you know immediately which part it is. But if you're an algorithm, you need to tell what outlets you need to use. So we have like a fluid dynamics atlas that if I know where it is, I know what inlets and outlets I need to put, right? So that is also data-driven. And this doesn't use deep learning. It's interesting because it's like 8 variants of 8 different topological variants of the circle of Willis, all of which of them are biologically correct. It's people who are healthy. So it's a graph matching between it's a partial graph matching between your image and 8 possible templates, where you need to estimate the likelihood for which of those is the correct one. And then you have something like this, that the colors means the position you have. And then one other thing that we're doing at the minute, and maybe I can do this experiment with you and see how it works. You need to put almost the light out to be able to see. This is a Turing test, okay? Those of you in computer science know what I'm talking about. And those of you who are radiologists or who are into imaging may not know what the Turing test is, but you will be finding this amusing. So one problem is with trials in general is that there is a selection bias. So you don't do a clinical randomized controlled trial on people who are volunteers. You do that on patients, people who have a problem. So that has a selection of the testing towards people who are at higher risk. And that performance is not necessarily going to be translating to the general performance. That's one of the problems of those. So what we are doing at the moment is trying to use biobank data, like UK Biobank, where we have 40, 50, 60,000 subjects, all volunteers, to generate these virtual populations. The problem is, these guys don't do contrast-enhanced MRA, because you will have to inject the contrast, and these are volunteers. That's the problem of being volunteers. So what we are developing is deep learning techniques that actually map from a non-contrasted MR to a contrasted MR, so we can synthesize a geographic scan. So what you see here, can show you this. These are 2 scans. One of them is the real MR angiography, a phase contrast MRA from, say, patient X. The other one is the data from patient X as well, but not the angiographic scan. I'm taking the T1, T2, and FLAIR, and I'm generating a synthetic angiographic scan based on a translation network. And the question to you is, which of these ones is the right one, is the original one? Which one is the fake one? So to say one of them is fake, but fake is essentially synthesized. Okay? So, because if we can do that, then we can do angiograms for 40, 50,000 people. And then we can do, we're in business. These people are not selected for any aneurysm. Then we need to do how we synthesize aneurysm. That's another story. So the synthetic one, and by the way, this is another scan of the same guys from a different, I think this is a slab projection angiography. So the synthetic one is the one on your right. Okay? So this is quite useful also, and this is data driven. The whole physics, so the mechanistic part is the fluid dynamics, is the release of the devices, is the clotting models, because these are biochemistry and CFD. So it's really using both. Okay? I think we need to move on.
Yeah, no, if there is other question, you can also ask in Spanish,
Yeah.
if you feel more comfortable. Yes.
You told us that you can perform a Turing test in order to, for example, know when you have an image or when this simulation be synthesized or real. You can do the same for example the images. Do you have any? Did you use some kind of metric in order to do that? For example, I don't know, some kind of error, like quadratic error or something like that.
So this is the slide. So in fact, we haven't done the proper Turing test yet. It was a bit of a joke with all of you to do that. But we are actually working now with the radiologist that we will randomize the images and present it to her and make sure that we look at, with kappa statistics, basically what is the fulling rate. Yeah? So we have a kappa statistic of 0.5, that means that this lady can differentiate between these 2 images. That means that we're really good at faking it. But what we've done is the quantitative one. So this is a report published already, where we looked at structural similarity indexes, not only also for different types of inputs, so T1, T2, and proton density, or only T1 and T2, or only proton density. So we look at what is the optimal inputs. We also look at diameters. We also looked at, these are very small pictures and probably not super great to see from there, but what we are showing here is the surface-to-surface errors, because we have the gold standards from those images at every position within the circle of Willis. We also looked at things like what happens if I do fluid dynamics with the ground truths and if I do fluid dynamics with a synthesized one, because it might be that the anatomy is slightly different, but from a hemodynamic point of view, you don't see a difference. So these are actually saying that they are very much reproducible. So these are for the full CFD in an area for the gold standard thing, and from, I'm saying I'm thinking because I don't really see it myself from here, and from the synthetic one, and then these are two cut points where you see the cross sections of the flow in those areas, and they're pretty consistent. So we use metrics of anatomy and we use metrics of flow because ultimately we're interested in the flow.
Is there any other question? Nothing.
So, Alejandro, at the beginning you were also talking about complexity of more and more data. What would you see in future if you had like patient pathway information, like this patient had in the stand in another location, or had a pacemaker, or had a bypass? Do you see this possibility? I know it's very ambitious, but do you see these kind of possibilities that your model could take those things in future into account?
Yes, I mean, what I've been telling is that you can build counterfactuals effectively, right? So you can create counterfactuals. So if you know that there are certain things that are typical, so if you have a study that shows you that patients that undergo aneurysm treatment, 20% of them always have a pacemaker, or we have some other stuff going on. You could, then the question is how will I model that effect, right? How we model the coupling between them. And you can create scenarios, counterfactuals that represent that scenario. And this is what I'm saying, this is the only way if you want to do, we know the story of trials, but what happens if you do complex interventions like combination therapy, where you put a device and a drug, where you put two devices, a stent, like in the TAI work that I'm starting to do it at the moment, you put a stent and then you put a stent within the stent. So you put a valve and a valve within the valve after a certain amount of years. How many trials you need is combinatorial, the problem is the trials, because the trials are always single effect, right? And what you try to look is at combination. It just blows up out of proportions, but you could do that. It's complicated, it's more computational power, but we know how to do that, right? So I wouldn't know how to, I don't know exactly what would be the relevant thing in this case, but you can also do, and I'm gonna stop with this because I think you need, but you can also do in silico observation studies. We just published a few days ago a paper that validates our clotting model using in silico observational studies. So we created a library of anatomical models of the vasculature. We ran our model, and we demonstrated that the spontaneous clotting, without devices, the spontaneous clotting rate is similar to the one in the literature, which is a way to calibrate our model as well. But then the advantage is once you calibrate that with the population where studies are published, you can go to small aneurysms, to very huge aneurysms, where perhaps there is less publications done. You can do extrapolations of those. And these are not devices, it's just an observation study. Okay?
Just a comment, what I like a lot about this work, I don't know.
No, just go ahead.
Is we were discussing a lot with NVIDIA. When people use GAN to simulate and things like that, the problem is that they only go within the distribution. So you're just interpolating more or less, or maybe extrapolating, but you don't invent anything. But when you go towards what you're doing and you use, also physics and simulations and etc., you can, beyond just getting something from the distribution and coming out like a GAN, but rather to generate a patient, which is, I found it amazing. It's really interesting.
I better leave you to carry on because otherwise I'm taking your time.
Okay, thank you very much.
You have a question?
No, it was just point. Okay, so we continue now with our next and last speaker. So there were people sitting there. There are places here if you want. Nassir, your computer is which one?
It's here.
Otherwise, Alex. Something there. No, it's not. No. There it is. Okay. As I was telling, our last speaker is Professor Nassir Navab. Again, Nassir, same as Alex, is kind of these people that you, when you do your PhD in medical imaging, you will read a lot. That happened to me as well. He has been working on an amazing number of he's so really prolific. You can go and check his profile and see how many publications and interesting work are there, from registration to interventional imaging, and it's one of the people at the NICAI community who is pushing more about this completely assisted intervention, right? And building and tying this world of medical imaging with what we do in the surgery room. So with that, I would say, and he's also a professor at the Technical University of Munich, where he has his lab. Thank you, Nassir.
Thank you very much. It's really a pleasure to be with you here, and it's my first time in Buenos Aires. I was very impressed. So I'm going to talk about this, but before starting, so in our lab we do a lot of things, and I will try to go a little bit at the beginning about the philosophy of the lab, and it's a little bit related to the question of Alejandro. So I'm personally, actually, everything I present you is the work of a lot of students, and the generation of students both at Munich and at Johns Hopkins throughout the years. And I myself have 95% position at the computer science department and 5% officially at the medical school. And since about 5 years. And basically our labs are located at the hospitals, at 3 hospitals of Munich. So since I'm very interested in computer-assisted interventions, we end up actually doing a lot of things. Originally, when I came from Siemens Corporate in 2003 to university, I was not planning to have a big role, but then I wanted to do computer-assisted surgery. And very quickly I found out that in surgery you're punished by the weakest link. So if you're good in something, but you have a little default somewhere else, the surgeons will not accept your solution, and they are completely right in that, because the outcome of the patient is the most important. So we ended up having a bunch of groups. Within our groups, I also wanted, I believe, on something I read in '95 by Asada, which was in applied science, you can only succeed if you have a good portfolio between fundamental research, translational research, and radical research. And we try in the lab to keep this combination alive, which is probably the hardest things to do. But that's why we have a backup of fundamental machine learning or computer vision, but we have a lot of translational, and we also have a lot of radical around the chair. And we really are proud of the citation, not because this is a citation of the whole students, even if it's not my name, but because it's going up. It's systematically has been going up from about, I would say, 8,000 in 2010 to 65,000 now, and also this is the work of all of them. And these are the groups, and of course we have about 14 co-stars at all time. Currently 2 of them from Latin America, unfortunately not from Argentina, one from Chile and one from Colombia. Now, when I talk about data science, we also have a center of data science like you in Munich. I always think people, machine learning in the last 10 years has been pushed a lot with the computer vision community and Google and Microsoft and et cetera, et cetera. And first of all, I want to make it clear. If you look at those images, which are the ones used in computer vision, they are about 7 billion people on Earth can annotate those images. Basically, any human can look and say, those are birds, this is somebody is riding horse, a family having dinner, somebody driving. Everybody, about 7 billion people can annotate it. As soon as you come to these images, now suddenly you need 20 years of education and 10 years of experience to being able to annotate those images. So we are transferring things from computer vision networks to machine learning is not as straightforward, or is not what we are going to do because of this huge challenge there. And if you now go to action, to videos, to things that are happening over time, in a teamwork, same thing happens. If you look at computer vision, they're looking at soccer, they're looking at autonomous driving, they're looking at a lot of events where, again, billions of people can annotate it. Now you come to this surgery. I filmed it about 15 years ago in Munich, and we have accelerated it. Even a surgeon cannot tell us what's going on. This was a spine surgery that because the patient had wants a surgery on the back, they had to do it laparoscopically. So even a surgeon cannot tell you what's going on. So really the challenge, a huge part of the challenge in us, and that's why I like the work of Alex a lot, is to bring knowledge, to bring physics, to bring doctors into the game. So one of my PhD students, Javad Tutuhi, who got some award for his PhD, at the defense of his PhD at Johns Hopkins a few years ago, actually told that he did a PhD in our lab for 5 years, 2 years in Munich and 3 years in Johns Hopkins, and he optimized a lot of functions, but he found out the most important function he optimized was this one, was having doctors and computer scientists co-located XYZ, spending a lot of time, but most important is the eye, to have the information that the surgeons and the doctors have, and the information a computer scientist has, to bring them, to optimize, to make them understand each other's and understand the modeling. So this is really what we try to do at the lab, and that's why most of our labs are actually located in the hospital, and unfortunately always in the basement of the hospital because places are very rare at the hospital. But this has been really our focus. We are really optimizing that function. And since about 10 years, we got a little bit more courageous. And we are trying to optimize a new function, which are machines and robots who think like a doctor, who collaborate with doctors, who try to understand how the doctors are working, who try to be at the same time in the same location as doctors, collaborate with them, and then try to share information to understand how the doctor is thinking. So I give you a few examples of our applications. They are more related to computer-assisted surgery. That's where we are really excited, and I have been always trying to get there. So I start. I do 3-4 parts of the talk. I hope I can manage it in the time we have. But the first thing I want to talk about is robotic imaging. And why robotic imaging? Because until 2000, since 1895, the invention of Röntgen for X-ray, and the first time we started to look into the body with physics, until 2000, our power of computation was not allowing us to do what we had to do in intraoperative imaging. If you look at MR imaging or CT imaging or PET imaging, what happens, the workflow or the requirement is relatively easy. You send the patient to a set of technicians, they prepare the patient lies in the MR or CT or PET, they take the image, and then after, the doctor in his office on the PACS system opens the image, looks at it, and makes a diagnosis. Now, the requirement of surgery is completely different. You have to, your hands is bloody inside the surgery, or your catheter is inside the body. So what you are trying to do there is you're only interested to see relevant information at that moment. You're not interested in a CT or MR classic, one part, etc., etc. You want to know how the physiology at this moment is reacting to my knife, how the body is reacting to the intervention I'm doing. Am I taking the right border of my tumor? You want to know what's going on. So you want to do relevant imaging. It has to be not only patient-specific, but process-specific. At each phase of surgery, you need other things to see. Time is no more resolution. In diagnostic imaging, time was resolution. Here, time is life. If you tell the doctors, I have an imaging for you, but it takes 25 minutes in the middle of your surgery, they say, forget about it. I'm not interested in it. So time is life, and then they are not sitting on a computer behind a PACS system and playing with mouse. They are actually in the middle of the surgery. So it has to be completely easy to use, which means it has to be intelligent enough to understand what you want. And then it has to be flexible, but at the same time reproducible. It has to be safe and reliable, and cost-effective. And for all of these things, until 2000, with our power of computation at that time, we could do nothing. That's why if you look at the interventional imaging, in the last century, it was still the same X-ray that Röntgen brought in. Ultrasound was not penetrating because you had to hold it with your hand, and you had to interrupt your surgery. You had laparoscopes which came from endoscopes looking into piping of industry. You were now looking at the piping of the body, but there was nothing serious, nothing intelligent. But since 2000, we are able to do more. And that's thanks to the power of computation. And the only solution in surgery, from my point of view, to do imaging is robotic imaging. Because it has to be an intelligent system which is doing my imaging, and then I am focusing on my action. So we'll talk a little bit about applications. So the first thing we did about 7-8 years ago, we started, I'm not talking about it, between 2012 and 2015, we started to do robotic SPECT and robotic X-ray and SPECT CT. Those things were easy because now we had a gamma camera attached to a robot, was doing the trajectory, X-ray was easy, we were not touching the patient. So it was successful, it was really interesting. We could do in 5 minutes a SPECT CT inside in the operating room. All those was published, but we got courageous in 2015. We started to say, let's do ultrasound. So this was one of the things, these are all published, and the codes, everything we do is public. This was the work we published in TMI, and the idea was that the doctor on the atlas of MR, just an atlas, would say, I want to measure this on the patient. These are all volunteers. Thanks to an IRB at Johns Hopkins that we then extended at thanks. So the doctor is telling me what he or she wants to measure on the patient in real time, and now the robot goes automatically. Thanks to an RGBD reconstruction of the body, it does a rough registration to the MR to the atlas of MR atlas, and does an acquisition of the patient. So if you come to our lab and you sign a little consent, you can actually lie down and we can measure your aorta. And we also now have it for the thyroid. So the robot goes in, does the 4D, and now one of the challenges here was how a sonographer optimizes the acoustic window. If there is not enough gel, if the pressure is not correct, the sonographer is intelligent enough to optimize it. How does the system do it? So thanks to the great work of Ateneos in 2012, what we developed is what we call the confidence map, ultrasound confidence map, which computes the physics and tells you at each pixel is the confidence of ultrasound. Do I have the right acoustic window? Now again, we are going back to combining physics and imaging. And then at the end, we have a volume of acquisition. Then we do a deformable registration of this volume to the atlas. Then we take what the doctor wanted to measure on the atlas and we map it into the ultrasound. And now we have this deformable registration of ultrasound and MR, and then we can measure what the doctor wanted to measure. Now, being at the hospital has this advantage that once per year, what we do for a whole week, my students come at 6 a.m. at that time, but that week, usually they come at 10, but at 6 a.m. they come, we prepare Weisswurst, which is the traditional Bavarian breakfast with pretzel, and we offer all the surgeons and doctors to come and have their breakfast in our lab in the basement. And at the same time, everybody is running their demo. And so two of the surgeons, when they saw this demo, and actually one of them, she lied down and said, do it on my body, and we did it, then they told we can use it in real surgery. And they were courageous enough, both of them, Anna and Yumi, they got actually the ethical approval for patients, and we directly went to patient. So the idea was they were telling when they do facet joint injection in patient in the spine, they use X-ray, and X-ray is not optimal. So they wanted us to do intraoperatively the 3D ultrasound with the robot, and then they would choose the facet joint, and then the robot would position the ultrasound and an attachment such that they could insert the needle and do facet joint injection. Both of them, they worked to get the ethical approval. They did 5 patients and 20 injections. Everything went well. We were verifying it at the end with X-ray. They had ethical approval for 25 patients. After 5 patients, both of them, one got a high position in Charité in Berlin, she left. The other one in Vienna, she left. So we are still trying to continue, but we did the first 5 patients with them. So this was the very first patient. So the idea was the doctor was telling, this is Anna. She was telling, from here to here, I'm interested to get the 3D. And then the robot was automatically acquiring the volume. This is now, from now on, is accelerated, but it was 48 seconds. You see it in 8 seconds. So you will see that the system would get the volume. And then we were visualizing the 3D volume to doctors, and then they were defining the facet joints. You will see next that in ultrasound they could nicely see the facet joint, and then they would define the facet joints, and they would say, this is the injection I want to have. And then the robot would go automatically to the right B mode that they had selected, such that the attachment is aligned with the direction they defined on this ultrasound. And then they would inject the needle, and then the robot would go away. You'll see in a second, the robot would go away, and then they could do the injection. And we were doing it for ethical approval. We were doing it a verification with that. So this went for 20, and it was really, really interesting. So our idea was then, can I do it fully automatic? this is a simple case. This is not a complex procedure. Can I do A to Z automatic and only visualize it to doctors? And we started to find out, okay, it's not as easy. Usually doctors look at the images and touch the patient to find the right vertebra. So we said, can we use machine learning and robotics to do that? And this was a work by two of our students, Maria and Maria actually. And now the system automatically combines both the pressure measurement and the image and the confidence map and tries to count the level of vertebra that you're looking at. And this is really like a human. We are trying to understand how the human works. So then it goes to the level where the doctors wanted to do the facet joint. Then the robot rotates and makes a better image of that particular level of vertebra. And then again, thanks to machine learning, we will do the detection of facet joints automatically this time. And the last remaining point is the injection, which has to be collaborative with the doctors. At our lab, we do a lot of imaging, and we are robotic imaging guys. We are not action robots, so we collaborate now with DLR, another center, Deutsche Luftraum, where they do robots for actions, and the idea is to do the first fully automatic injections. But there, as I show you later in my talk, visualization becomes very, very important. I was in a panel with Philip Xu, who is one of the best surgeons in the world doing Da Vinci in Hong Kong. And somebody asked him whether he would use automation. If the robot can do automatic part of surgery, would he let the robot do that? And Philip answered really nicely. He told for the last 5 years, he has a BMW, and when he bought it, they told him that if he push a button, the BMW automatically parks the car. And he says in the last 5 years, he had not dared that, to push that button. And I told him, so if you push that button, but the system shows you that it sees the top view of the environment, it shows you the trajectory the car is taking, it shows you that it recognizes everything, would you push that button? And then his answer was, now you're talking. Yes, maybe I push that button. And this is exactly where I personally believe, where the title I was telling from intelligence amplification to artificial intelligence, if we cannot show them what we are going to do, if the system does not show them, I am fully understanding the physiology, I am fully understanding the pathology, I know what you are going, I have a good understanding, then they would not let it go. But if we can visualize and show them that we have the right knowledge, then the system will do it. And that's why I believe in the next 5 to 7 years, intelligent visualization becomes a very important issue in computer-assisted surgery. So now when we start to understand how it's good, we started to do vascular after that, because we lose Yumi and Anna, as I told you, while searching for the replacement surgeon partner. We started to work with 2 vascular surgeons, Dr. Gottlieb Hospital and Pausing in Munich, and Carlos in our hospital, and we tried to go towards vascular. And here, the challenges are a little bit different. So one of the challenges is motion. And this was rather easy, so the idea was, can I compensate for the motion? And the answer was yes, we could actually compute again, with computer vision and machine learning, we could get the surface of the patient, and if the patient was moving, we could do a mapping of the cloud of points and try to compensate. Even if there is a big motion like here, the system would understand the motion, would compensate for motion, and if it was needed, the robot would do like a sonographer, move back and would do computation. Now, in which when I tell you why I believe robotic sonography would definitely be better than sonographers, the only reason is when a sonographer does all the work, they're really intelligent, they do a lot of things, but like us and Google, they have access in their memory of what happened, but they don't have direct access to that data. But a robotic sonographer would have access to the exact numerical value of all the data it took and the orientation it took. So at some point they would be better, the way, Google has more information or can do better search than us. So now we were doing motion compensation, and we were showing that the vasculature would be much better reconstructed if we do that. And then we started to be a little bit more courageous and go towards deformation compensation. And now it's a little bit more complex because now we need to compute this deformation dynamically and try to compensate for that. And now we are actually doing that using a combination of machine learning based optical flow estimation, but also then going to compute the elasticity of the tissue at that point, also taking a look at the CT values, and then try to combine all of this and do a compensation. So what you see on the left-hand side is deformed vasculature. What you see on the right-hand side, it would be if I take the image in water, so which means no deformation, and in the middle is our correction. It's not as perfect as the ground truth, but we are getting very close towards that. And this is, now this compensation, usually sonographers do it in their minds, but now we can start doing it in the minds of the machine, thanks to those computations. Now, again, very similar to the work that did the start of the work, not as complex as what Alejandro was telling. Here, working with X-ray has one advantage is that we can do some labeling in CT. And because the physics of CT to X-ray is much, much easier than ultrasound or MR, we can actually, if we can do good simulation of X-ray, then with a very few annotation on CT, we can generate hundreds of thousands of X-rays which are annotated. And you can annotate anatomy on X-ray that you don't see because you have annotated it in CT. So we started to do a series of work in that direction. The first one was in 2016, when we started to see, can I take an X-ray? And then if a radiologist look at the chest X-ray, they can ignore the ribs, they can ignore the spine, and focus on the lung. Can the computer do that? Can the computer get rid of the, all the images of the spine in front of the back? So can I take an X-ray and get rid of these layers? And in order to do that, we started to take CTs, create an X-ray from the CT, then decompose the CT in three parts, the front part, the deformable part, the back part, and for each of them generate an X-ray, and say, can I go from this X-ray to those three X-rays? And then we started to do that and train the network that if I give you a chest X-ray, I'm interested in the middle image, and I want to get rid of the first and last one, and the system got trained, and the way we validated it, it was very interesting. We took a database on the website, on the public site, where they were looking, using chest X-rays for tuberculosis diagnosis. And what we did, instead of that image, we only get the middle image, and we could increase the performance of that network, which has nothing to do with us, by 8%. And this was really interesting. This is a MICA 2016 paper. And then we started to find out that the quality of the X-ray generation is crucial. So we generated this DRR that actually is, again, the code and everything is available, which is a mix of machine learning and physics. So in the first layer, we take the CT, we use machine learning for segmentation of the tissue, In the second layer, we use completely physics of X-ray to go from CT and tissue-based to generate the X-ray. And in the third one, we add the noise, again with machine learning. So where we needed machine learning was at the beginning and at the end, and in the middle we use the physics, and then we are able to really generate X-rays which are much more realistic than the X-rays. And then we started to do some annotations of doctors in 20 CTs, and only based on those landmarks we could annotate about 500,000 X-rays automatically. And by doing that, we were able now to detect on those X-rays, in 70–80% of the case, we were able to detect the landmarks on the X-rays. This got the Mikai Award in 2018 and ID Cars Award in 2019. But 80% isn't enough. And the answer is yes, because then what I can do, this is a continuous work in TMI, is that now we did it a fully automatic system. What happens is that the patient comes, does the CT. We generate a lot of X-rays out of it. We run our algorithm, which means on 80% of those X-rays, we can detect those landmarks. Now we back project those and reconstruct those landmarks patient specifically. We make sure they are on the anatomy, and then we retrain the network patient specifically. This is all automatic, and now we are able to patient specific automatically do the registration. The most important part, which is the initial registration, followed at the end with the before level. And this is all thanks to really power of computation and machine learning that we could now do that automatically. So the last part, there are two parts still. I don't know how much time do I have. I have now, perfect. This is a collaboration with Greg Osgood and Alex Johnson at Johns Hopkins. They were really fascinated by augmented reality. So very quickly, I think you're academic, you all know, augmented reality was not invented by HoloLens. So basically, in medical augmented reality, the very first work was 1989. In neurosurgery, actually, they started to include vasculature segmentation into the image. This was the very first work. Then in 1992, Henry Fuchs in North Carolina and his team, they got encouraged to do a head-mounted display to visualize ultrasound on the patient. But don't forget at that time, the power of computation was 386, so they couldn't really do it and everything. But 8 years later, Frank Sauber at Siemens Corporate Research with his team, they really created the first augmented reality system in medical, which was the ideas of Henry Fuchs, but the amazing work of Frank Sauber, Ali Kalman, Sebastian Vogt, where they created this video see-through augmented reality system that could really work. It was costing 50,000 euro at that time to build it, but it was functioning beautifully. What, however, HoloLens did 15 or 20 or 30 years later was to go to the big market and make it, 3,000 euro HMD, which you can buy instead of 50,000 euro of Siemens Corporate Research at that time. And so doctors like Greg and Alex right away had bought 5 of them, and they were very excited. So we started to work with them, and we did the funny things that they really like. That X-ray system, if you pay attention, has the HoloLens attached to it. Not because it wants to see through the board, but that X-ray system is calibrated with the HoloLens. Now the nice thing is that HoloLens is the master for the HoloLens which is on the head of the surgeon. Now, that HoloLens which is pre-calibrated with the X-ray, when it takes an X-ray, knows the physics of X-ray. So the doctor actually, when he takes an X-ray, can take the X-ray and bring it to the patient. can see where this X-ray is projected from where. You will see in a second, Javad takes the X-ray with his hand and brings it onto the patient. Now, this simple thing changes a lot of things for the surgeons. They really, really loved it, so they could do tons of applications. This is again another TMI, where they could actually look at all the surgeries, all the X-rays they took during the trauma surgery. They could reposition their systems, they could do implants, etc. I show one example of it with Greg Osgood. In the whole example, Greg Osgood is only using an HMD. Alex Johnson is looking at the X-ray to make sure everything is okay. But this is the nice thing you will see. So Greg Osgood takes the X-ray in his HMD, and now he defines the entry points and the target point. He says, that's where I want to enter, that's my target. And he does it on 2 images. As soon as he finishes defining the entry and target point, then he looks on the patient, in this case it's a phantom, and you will see in a second. I'll tell you later, he hated this interaction. But when he looked at the patient now you will see, he sees the entry point, he sees that he defined on X-ray, now he sees it on the body and the target point, he sees where he has to bring his drill, and now Javad gives him the drill, and he only has to align his drill with the virtual drill and start drilling in. And now you see the problem of alignment if you see Greg on the left-hand side, because the alignment is 2D, even though he's looking at 3D, he has to go down and up. And later we did a bunch of very interesting work in augmented reality where you have virtual mirrors such that he doesn't need to go down and up. He can see the scene from multiple view augmented, so he can do the alignment. But this was the first work, he only used the HMD to do the whole thing. And Alex Johnson was looking at the X-ray to make sure that he's doing it fine. And at the end, they verified with the X-ray that everything is done correctly. So, the more of this kind of augmented reality we do, the next would be that the robot does the work, but the doctor can see everything that the robot is seeing, the robot is doing, and etc. Now, a little bit more ambitious, if we want to do augmentation in endoscopic surgery, it's more complex. This is actually now a few years project collaboration with Konrad Kraus, a surgeon in the other hospital of the Munich. And then we started to do that. It's a huge work of registration, calibration, visualization. At the end, we were able, these are 20 peak studies, I show you the view of the whole thing later. We could actually augment the view for them during the surgery and show them critical structures. And they could manage to move better. Even though, as you see, we're not doing dynamic, this is intraoperative X-ray, segmented, visualized on top of the endoscopic surgery. Now, during this whole work, we found out that in surgery, one of the problems is that there are only, usually I say, there are only 2 people in the surgery room that they know what's going on. I go back to the same surgery I had shown you. In such a surgeries, usually there are only 2 people knowing what's going on. One is the head surgeon that can have a full holistic understanding of what's going on, from patient inside to the procedure to the tools, and usually the head nurse. Usually the head nurse, after 20 years of experience, she sometimes knows much more than the surgeon. I've experienced it firsthand because I was in the operating room several times, and then I was asking first the surgeon, how long do you think this surgery would take? And the surgeon usually would give me a standard thing, like 45 minutes. And then I was asking the head nurse, and she was telling me, "Oh, this one is complicated. It will be 1.5 hours." And it was 1.5 hours. And I did it several times. So they are very, very well. And their role is very important. Stores came with a system which is voice-based. And our surgeon, Voicner, got it. But after about 6 months, he was not using it. And I told him, "You paid so much for this voice-based system, Stores One. Why aren't you using it?" He said, my nurses, after 5 times I tell them to do something, they know when to do what. This stupid system wants me every time to tell, turn on the light, turn off the light. He doesn't understand that's the moment it has to turn off the light. But the nurses, I don't need to tell anything. Even if they're new, after 5 times they know. So our system are stupid. Our system has to become intelligent. In order for that, we have to have a semantic understanding of what's going on inside the brain. And that is our focus for the next 10 years. We started a few years ago. This time I did something I'd never done. I first wrote a white paper, put it on archive, and then I approached a few industries and I told, we want to do this. There's nothing to patent. There is a white paper on the archive. So if you want, you can sponsor it. And now we are sponsored by 3 competing companies, Stryker, Johnson & Johnson, and Storz, on the same project. But everything is already on the white, but they know that they can use it in their technology. So what do we want to do? We really want, the surgery is focused on the patient. But if you do a computer science domain modeling, you would say there is a surgical workflow, statistical surgical workflow, which would change based on the patient. There are human roles, but there are also a lot of devices, and each device has its own digital graph of what to do at which point or what to visualize. The difficult point where humans come in are the mapping tables. At which moment of that statistical representation of surgery, who in this human role needs which information or has to do with the action. This is the hardest thing. This is the understanding of chief surgeon. So in order to model that, we started to get inspired by movie industry and graphics. So 30 years ago, they started to do what? They started to have scene graphs explaining the movie, and then let characters play the movie. If you go on Pixar's website, you will see that they have the scene graphs, that they define the scene graph, they define the interaction, and then the movie is generated. Now, in our case, we want to solve the inverse problem. That's much more difficult. I want to look at a surgery room and actions, and then generate the scene graph out of it, so I can reproduce it if I wish, or I want to understand what's going on. I want to have a full understanding. So what we started to do about 6-7 years ago, but mostly in CVPR and ICCV papers, first in computer vision, first was taking 2D images and then going from 2D images to graphs. This was also 5.5 worked on it, and a lot of other people, including us, to do 2D from scene graphs. But we wanted to go more and more to 3D, so we started to do again in CVPR a series of work where we started to do 3D scene graphs, and we also generated our own 3D scene graphs. But then this was the bread and butter of that archive paper I was talking to you. The idea was, if I can do the 3D reconstruction of the board, if I can segment that based on machine learning and computer vision, if I can now in this 3D world, which is a bad acquisition we used at that time from Strasbourg, I can detect the patient, I can detect the monitor, I can detect the X-ray system, I can detect the people, and then I can start to build my graphs. Now the nice thing is that I can choose, if I'm a producer of an X-ray system, my graph would be centered on the X-ray and how it interacts with people. If I'm a surgeon, I'm interested in patient and the surgery and my interaction with others. my graph would be different. These graphs are going to be complex because some of the actions, some of the links are direct, some of the links are virtual, like I'm looking at the display by doing an action, and etc. The first thing we started to do is that we use this to create a summary, an intelligent summary of the surgery. And we can generate it for any of these surgeries now. And now we can start to do semantic mapping of the surgeries, but at a real semantic way. And we can also start representing, this was a presentation we started to do based on, for example, if I'm interested in the CT system and how the people are interacting with the CT system, then I can start to do a synchronization of two different surgeries based on different things. I know I can also say what's happening at one point, and once I do the synchronization, I can say I'm more interested in the patient or more interested in the CT, and then I can synchronize two different processes completely based on, for example, the use of CT, or based on an action on the patient, or based on the interaction of the crew. Now, as we started to do more work, we found that the data available was not good enough for this. So we had another series of work, another big project with Simon Weider on telemedicine, and I just show it to you just to see because we used it later for our process. You can't hear the sound, but it's in German anyhow. So the idea is that the surgeon is remote at home with virtual reality headset, and the trauma surgeon, young trauma surgeon, has a HoloLens. The remote surgeon is looking at the 3D reconstruction of the environment and is explaining the local surgeon what to do. And the local surgeon is looking at it on the patient with HoloLens. So this is the view of the local surgeon, this is the view of the remote surgeon. So the remote surgeon is looking at this reconstructed scene, and then is explaining to the local surgeon where he has to do his cut. And the local surgeon was the first view you saw. The local surgeon is augmented to the head mounted. The remote has a virtual, the local has a real, and then later with Derek Wilhelm, we got a project during the COVID period to visit the COVID ICU virtually, so the doctor does not need to go to the room, but being able to discuss, and there is a sort of attention, interesting things here. The remote doctor can take any piece of the room dynamically and take it in his hand. In this case, Derek took that screen, wrote it into his hand, and started to annotate to say, this information is interesting, you look at this, measure that, etc., and the other surgeons was watching. Now, why I'm bringing this? Because this nice project allowed us to do full 3D reconstruction of the environment. And we used that to actually, when we did the 20 surgeries of pig surgeries with Conrad Coase, we could do the full reconstruction and everything synchronized for all the data we had. And this also generated a set of data that we anonymized, and we had to do some anonymization in order to be able to actually use the data or publish the data. But now, we can start, even that data, unfortunately, because of anonymity that we needed to do, we could not use it for SINGRAPH. So we started actually to generate our own data. We generated a set of surgeries, simulated surgeries, based on the real scenario of the surgery. And then we made the whole public data publicly available in last week. And basically now what we can do is we can generate automatically the SINGRAPH of what is going on. And those SINGRAPHs that are automatically generated are given to a network, and then the network makes a decision about what is going on, which actions are going on, who is doing what. And the network starts to understand. semantically what's going on. This is going to be a very long-term project. We already got the second paper in this direction now. This was last year. Now we have the continuation of that, which got early accepted at MICAI, where we can actually do a temporal matching and understanding of what's going on. And then in last MICAI, I go fast, we started to give these temporal scene graphs and then try to predict what's going on and the roles. You can say which actions are happening. We could show that some actions are easy, some actions are much more complex because are not easy to find out whether they are touching or they're cutting or they're assisting, but the system is intelligent enough in those cases. And basically now since then, together with the Striker, we are taking real patients with the micro robot, but with cadavers and phantoms to do. We are acquiring a lot of surgeries. They agreed again that we make everything public. And now the first application which is coming is that I have scene graphs from non-robotized surgery, I have scene graphs from robotized surgery, and now I can find out why a robotic surgery, usually, a surgery, if it takes 40 minutes, when you do it robotically, it takes 2 hours. And this has blocked everything. The company, the hospitals, they buy the robots because it's a good advertisement, but they can't go every day instead of 8 patients with 4 patients. So they do it only 1 or 2 days per week. But if we can find out where is this problem is coming, how we can optimize the workflow, such that we can do it as fast as the regular surgeries, everything will be much more interesting. So I really like this caricature of Einstein's simplified book, which says, it may not be a perfect wheel, but hopefully it is a mistake. This was the video we were showing that dynamically the system is trying to understand what's going on and generating these scene graphs and then mapping it to what he had learned over 20 surgeries for neurosurgeons. So I finished my talk now with one advertisement. Every 2 years we organize a really beautiful summer school in Zurich Hospital of all Greece with 24 surgeons, 24 from industry, almost all the industries were involved in medical, and 24 academic. The academic, we took it, usually we have about 100 to 150 applications, we have to take 24. We try to look at diversity, so if anybody from Argentina applies, I think we will take at least one from Argentina. Surgeons, we take all of them. Last time we had surgeons from Africa, from UCLA, from Montreal, from Belgium, 3 from Hong Kong, 1 from Japan. So surgeons, whoever applies, we take them. Industry, we take them because they are paying for it. So they are industries, they sponsor us because they also pay $3,000 per person. For the rest, for surgeons and students, it's free to participate. We are, thanks to the other costs, we are taking over their costs. We don't pay the cost of them getting to Zurich. So you have to get to Zurich. From here is a little bit more expensive than other places. But if you're interested, please apply. And it's really great. We are at the hospital there. So the whole crew also visits all the operating rooms and they explain them, etc. And then there is 5 days of summer school where the best in the world is starting actually this year with Henry Fuchs, going through Mark Polyphis from ETH in computer vision, Federico Tombari, a lot of Terry Peters. We have 5 days of teaching and then 1 day of break and then 5 days of hackathon. In each group there is 1 surgeon, 1 academician, 1 industry and 1 of us as tutors, and there is a 5 days hackathon. So I encourage you to come. Thanks for your time and I'm open for questions. This is something we did for public for many museums, But now the medical school of JSU and TU also are using a more complex version for teaching. So I leave it in the background. Thank you for giving me.
Thank you, Nassir, for the amazing talk. These are really insightful, I think, ideas that you're implementing there, technologies. So is there any question from the audience?
I have a question.
Yes.
I want to address the medical professionals, and I want to just have a glimpse of how much all these astonishing presentations from Professor Alex and Professor Nassir sounds science fiction for us, for our country. I mean, how far are we from all these developments that are still underway, but for sure would sooner or later come closer to us? So that is one question to the public. If any of you might respond.
No sergeants? No sergeants. Doctors. I don't know. What do you think? So I think that we have been, it's not science fiction at all. I think that the problem is how to implement it and as you were telling us, when you can use it and it's practical and it's, you can do it in time that efficient enough. The other thing specifically about the Argentina is its cost. More importantly, when you're thinking about robotics, like acquiring those machines, it's difficult for us to have updated machines in hospitals, and if you're thinking about like new developments that has new infrastructures, I think that's a difficult part. But I don't think it's science fiction at all. I think we will start using this, and we are using these technologies nowadays, and it will grow.
One of the problems, going back to what Alex was suggesting, is that these days, at least in Europe, and in Johns Hopkins or Harvard, other places, they started to understand that the technology has to be integrated into the teaching of the medical school. It's too late to, my wife is a dermatologist, she's a medical doctor, but whenever I present her our work, she tells me, can I use it today? And when I say no, she said, I'm not that interested. And it should be like that, because they have to take care of the patients. They don't have time to play with something new. So 95% of our doctors have to take care of our healthcare. There are only really a low percentage that in university hospitals they have the luxury to play with new technology or introduce the new technology. Then the teaching and training of the people who are actually doing the surgery to do a new technology is costly in time, in healthcare, in everything. So the key is that the medical school has to have professors who are technology professors. And then within the study of the medical school, I know they are studying a lot of things, but they also have to study and play around with the new technology. At JSU and TU, it has started. We are teaching machine learning to medical students, and they're extremely good in it, because usually the medical students are the best of the high school, also in math. It's not like they're not good in math, and they're not good in science. So we do it, they are really good. They implement things in Python much better than my computer science students, so they are okay. They're really good. They are not doctors, they are second year or third year medical students. Same with robotics at Johns Hopkins. Jeff Swartzen, who now moved to Texas. He started a course on surgery, which we also have in Munich, where half of the students are medical students, half are technology students. I think this is the future. If we are expecting doctors to take off patient time and learn new things, we will not get many of them because they have to take care. They are so busy. Most of this, like when I was talking about Anna and Yumi, the time they were coming to our lab was after a whole day of service. They were taking their personal time, half sleepy, coming to our lab and discussing with our students. So it's tough. It's tough for doctors to do that, and you have to think that whenever you are thinking about a future patient, you are taking off the time of the actual patients. So for some of the doctors, I think this is a dilemma. So I don't know if the medical schools at our university until about 5 years ago, we didn't have any computational professors within the hospital. They were in computer science like me. Since then, we have now 7. We have 1 in pathology, 1 in orthopedics, 2 in radiology. Daniel Wickert came to radiology. 1 in nuclear medicine, 1 in ophthalmology. So I think the medical school has to start having computational professors and integrate some technology teaching inside. Otherwise, it's very hard.
And I think Marissa's point, which is that point is about culture. And I think your point was also about cost. They are related because I think, at least with the examples I gave on the regulatory aspects, you realize that we're spending lots of money for suboptimal treatment or for evidence that will never be used in certain countries. So if you actually have people who have this more interdisciplinary training, I think they're able to see much more efficiently those gaps in knowledge or in efficiency at addressing them. Personally, I think if there was one suggestion for the center here is create some sort of sanctuary for people to actually connect between engineering and medicine, because that's really important. That's where a lot of the conversations happens. Teaching in students is a way to do that, because if you, for instance, create degrees here which are taught by both professions, you have already a flow of clinicians coming in, and then once they're here, there is possibilities to work on projects. But you need to create that flow. I mean, there is nothing as good as bumping on each other, on a coffee machine or whatever you bump on the mate here. But you need those points of thinking together to address some of the problems which are really.
We have some important, I think, stakeholders of these here today. Like there are many bioengineering students here, and I think they are a good kind of, they receive teaching from both. I think there are some professors here, so yeah.
Yes, I think that Silvia wanted to say something because she's from Ciudad Universitaria institution, which is really relevant and one of the most important institutions in Argentina.
I'm a pathologist, medical pathologist, Hospital Italiano, here in Buenos Aires. I agree with him. Now in pathology, we are making telepathology many years ago, and now for digital pathology, we are beginning with the validation of the scanner for digital pathology. And robotic surgery is 10 years ago, or less, and doing very well.
So you're implementing
robotics, yes. And artificial intelligence in radiology 5 years ago.
Yeah, I think maybe what you were commenting here are like next steps, right? To incorporate and augment wherever we have maybe. Because many of the technologies we're showing there, like augmenting reality, at least is not always present, right? The robotics that are changing. So that's great to see. There was another, I don't know.
No, we have a big informatic
department, yeah.
fundamental.
Yeah, Shiva, like the project you have there. So at the Ciudad Italiano de Buenos Aires, they have a big department of artificial intelligence in medicine, and they are doing amazing. Actually, one of my PhD students is there. Two.
Yeah, I think that, well, one of the main issues that we still have is that our gold standards are the specialist opinion. I come from a neuroimaging background, so we have a lot of people even in Barcelona, in Bariloche, trying to get the perfect algorithm by, to diagnose a dysplasia or an atrophy just by looking at the MRIs. And although there is a lot of coincidence, the last word is always the radiologist, who, just for a question of